All right, good morning.
Morning.
How's everyone doing today?
I'm stressed. I have a midterm later.
Physics or calculus?
You.
Oh, yeah, that too. Yeah, there is that midterm. Oh, and engineering 250 in an hour, extra bonus.
Yeah. But that's with his odd. It's not too bad. He makes it a pretty decent test.
Okay, cool.
It's pretty relevant to the court, you know.
Yeah.
Got a lot of trick questions and stuff.
Cool. All right. Well, send me an attendance note. The 15 of us who are here. And I had a request to go over some aspects of makefiles, so I want to start off by doing that, and then talk a little bit more about PA3, and then switch over to talking about GDB. But any questions outside of those?
I had a small question about best practices involving like defines, whether or not they go in header or if they should be relegated to whatever C file they're only in.
If you're only using it in one C file, it might make sense to put it in there, but it really depends on what the define is. If it's something that, you know, might be, if it's something that's never going to change, you know, and you just don't want to hardwire a magic number, I would just put it in the C file where it's used. But if it's something like, you know, in a high-low game, for example, the default high and low values, if the person doesn't have any arguments, I would probably put that in a general header file, so that, you know, if somebody downloads your game and wants to make changes to it, they can look at that one file and there's a comment that says, you know, to change the default range, set the following two variables accordingly. So that kind of thing. I don't know what best practice is, but I think it just kind of depends on the specifics.
Yeah, I was reading through, and I think as far as the program goes, I can understand most of it. The makefile, though, is just kind of an enigma to me. I've never really looked into them, and obviously I understand the whole point behind it, but where it says, like, it should clean the appropriate main and .o files.
Yeah.
That part, I just kind of didn't really fully understand it.
Okay, so yeah, let's go over makefiles. So here's a sample project. It's different from the pieces that we had yesterday, but you know, I've got a bunch of .c files. So there's a display function, a getAnswer function, there's an intro, and there's the main program which calls all of these different functions. And there's a header file, main.h, that includes standard I/O, prototypes the different functions that are in our project, and also just defines a symbol called magic. It's just some magic number I didn't want to embed in the code. And so, you know, I can certainly build my main program by just doing this. And star.c will expand to, you know, this list of files. And so this will say compile each of these .c's and link them together into a main. And that'll work. It's a good, quick, and dirty way to build your executable, but it's inefficient, right? So we make this makefile, which has these targets and dependencies followed by recipes. And so if we just say make, or if we say make main, it will say, okay, to make this I need to have these 4.0 files. And if I have those, then I'll do this command, which is efficient, to link those .o's together. And so the first time that I say make, you know, there's no .o files here anywhere in sight. So if I say make, it will have to build those .o files first. So where does main.o come from? Well, it comes from main.c and main.h. And if it has both of those, then it does this to compile main.c into main.o. And that satisfies this dependency. Then it says I need intro.o, and to do that I need intro.c, main.h. If it has those, it'll execute this command. So that's why it did these 4 GCC commands. And then after that, all of these dependencies were satisfied, and so it executed this command. So if I say make again, it'll do nothing. It'll say everything's up to date. But if I change main.c, just add a comment in the beginning, and I say make, it'll go ahead and it will recompile main.c and then relink my .o's. Right. The efficiency is it did not recompile intro, display, or get answer. Those were already compiled into .o's. And yeah, the targets are like labels. So if I just say make, it tries to make main. But if I said, for example, make intro.o, that would do what it needs to do to update intro.o. Well, it's already up to date, right? But if I touch it and then I say make intro.o, it'll go ahead and re-execute the recipe for making that that particular target. So the clean business is kind of a bogus thing, right? Because we're not actually building a file named clean. We're tricking the make utility into saying, hey, if I say make clean, I want you to do this, right? This is not compiling anything. This is just deleting a bunch of files. But the effect is, you know, if I look right now, I have my .o files, I have my main file. If I wanted to force everything to be recompiled and I say make, it doesn't do anything because, you know, everything's up to date. So if I want to force it to recompile, I have to get rid of these .o files and I have to get rid of the executable file. So I have this kind of bogus target in here called clean, and if I say make clean, it should say, okay, I'm going to do this. And so make clean, and it does that remove, and now all of those files are gone, and if I say make, it will recompile every .c file and then link all of those back together. And this is really useful, for example, when you move from one machine to another, or if your operating system updates and some of the libraries have changed from one version to another, or for any reason you want to force it to rebuild your project from scratch. So most makefiles include a clean option, which will get rid of everything that might have been made. But you know, we can put anything in here that we want. Right, we can put an echo statement in there followed by the remove. And now if I say make clean, it'll say, you know, cleaning up stuff, and it'll go ahead and remove the files.
How does it know, like, so make is a built-in command that can just kind of parse the info that's in makefile, and it knows that if it's not indented, it's like an argument that can be made for it?
Yep. That's exactly what it is. That's a perfect description of it.
What if you have, like, multiple lines of files to compile in, like, your main in the makefile? Do you just format that by putting them line to line and indenting it?
So you can string everything out in one big long line. You can put semicolons to put multiple things on here, and I think you can also use a backslash, maybe. Let's see. does not like backslashes. So I think you just string it out in one big long line. Oh no, that's okay. I broke something. Yeah, so you can do that. And that's a general Unix kind of thing. You can put a backslash and continue a command on the next line. And that seems to work most places. And you can use makefiles for anything you want. It does not have to be just for compiling C programs. If you're doing text processing, so there's a whole text processing system inside Linux called TeX and LaTeX, and building a document from source usually involves several steps: pre-processing your TeX file and building a bibliography and an index and putting those together and converting the output to a PDF. And you can make a makefile to do that. And then in your directory where you're working on your document, every time you want to create a new PDF from what you're writing, you just say make, and it does all the stuff that needs to be done. So it's a very general purpose utility anytime you have a series of commands that need to be run, particularly where the commands depend on what's been updated and changed, and you need to do certain commands on certain files because they've been modified. Makefiles work well for that. All right, and this is on the Linux server under a make stuff directory. All right, so let's look briefly at programming assignment 3 in terms of program flow. And I want to just kind of think from a higher level, right? If you haven't gotten very far on the high-low game yet, or you're not sure, how to get started or something like that, let's think about what's really going on in here. So if we read the description from the assignment, we can sort of translate that into an approximate flow chart. The first thing we need to do is figure out what low and high are. All right, and that's a whole day's worth of work in itself, maybe, right? That's not a day, but that's dealing with argc and argv. And if argc is equal to 1, then low is 0, high is 100. If argc is equal to 2, then low is 0, high is whatever argv1 is. If argc is 3, then low and high come from argv1 and 2. But to convert argv into an int, we have to use scanf, and we have to check the return value, and we have to look for extra stuff. All of that stuff, I'm just putting it in one little block here. Figure out low and high, right? And I'm not going to worry about the details yet, right? And yeah, low and high could be negative. That's totally legit. But usually not what we do. But
hold on, they can be negative? Like that's...
They should be able to be. I don't think it should affect your code at all, though. I think your code should work regardless.
Mine is less, or low can't be less than 0.
I don't think that's in the requirements. Let's go from negative 200 to negative 100. Oh no, low val is bigger than or equal to 0. All right. Yeah.
Yeah, I thought I saw that.
Yeah. Okay. I didn't go totally wacky. All right, so figure out what low and high are. Okay, I should remove that requirement next time I do this assignment. So figure out low and high, and then we play the game, right? Playing the game is basically a loop. So we have to make a guess, which is the average. And then we have to find out if our guess was too high or too low or correct. So, you know, was our guess too high? If it is, then what do? We adjust high to guess -1. And we go back and we make another guess. If our answer is not too high, we say, is our answer too low? And if it is, then we adjust our low. And this time we set it equal to guess +1. And then we go back and make another guess. If it's not too high or it's not too low, then the game's over. So if you start from, you know, a flowchart or pseudocode or something, right, this doesn't look like too daunting a task maybe, right? Some sort of initialization that, you know, says hello, figures out what the low and high are, and then this is a loop, right? So this can be coded as a while, you know, 1 = 1, a forever loop. This is a single statement in C, guess equals parentheses low plus high over 2. And then a pair of if statements. And we need some extra stuff in here. We need to ask the user, you know, here's my guess, is it high, low, or correct? We need to get an H, L, or C from them. But then based on what they responded, we can answer these questions. Was the guess too high? And if it is, do this, go back to the top. If it's low, do that, go back to the top. Otherwise, the game's over. Thank the user for playing and just return. So this we can ignore to begin with. We can just make 2 assignment statements. Low equals 0, high equals 100. Now that's ignoring the possibility of command line arguments and so on. But that will let us, you know, continue down to our loop, which is where most of the action is happening. And if you're just trying to get something up and running that plays your game, right, just hardwire low to be 0, high to be 100. All right, here's our while loop. Well, there's one piece missing in here. How do we know if the guess was high or low? Well, we don't. The user does. We have to ask the user to give us that information. So print guess. And then ask the user for high, low, or correct. All right, well, there's a lot of detail that goes into here. This is your whole get answer function, but we can do this pretty easily if we say something like fgets temp length of temp standard in. We can simply say if temp bracket 0 double equals sign quote H. That's how we can tell if they typed in something that started with an H. And we can say if temp bracket 0 double equals sign quote L. That's how we can tell if they typed in something that started with an L. And, you know, maybe for the sake of just getting this running, I'm just going to worry about those 2 cases. And if they type anything other than H or L, I'm going to say, okay, it's not high or low, the game's over. I must have guessed correctly. Right? Now this you know, doesn't get you 100 points on the assignment, right? But this is a stepping stone, right? This becomes trivial. These statements are just assignment statements. This is the only, you know, harder part of this, and you've done this a bunch of times already. Print something, do an fgets, and now these if statements are just checking character 0 of temp. And this will let you play high-low. as long as, you know, when it asks you for H, L, or C, you always type in an H, an L, or a C, and you don't make any mistakes, right? This will go through and it'll iterate on the guesses and so on and so forth. It doesn't predict how many moves it'll take. It doesn't do the cheat detection. It doesn't handle errors in here. It doesn't handle the command line arguments, right? But it's still got the core of the game implemented. And then you start adding more detail, right? So you say, okay, I'm going to, you know, deal with the command line arguments. So you pull out your notes on scanf and extra and return values and all that, and you code that and make that work. Or you say, okay, I'm going to, you know, write the serious get answer function, which will, you know, do the fgets and do the string compare to h \n and so on, and return, you know, an h, l, or c, and then I use that in my if statements. But almost always it's easier to sort of start with a structure of some sort and add detail to it than to try to sort of get everything working from beginning to end. And then, you know, makefile is something totally independent of the specifics of the code, right? That's something that comes in at the end, maybe. If you do it in the beginning, it's quicker to develop, but you can certainly develop your code without doing that. You can develop your code without breaking things into functions, right? You can do all of this in one main program, and then once you're at a point where you feel like you've got this under control, then you can go ahead and you can start, you know, breaking things into separate files, and then start worrying about how to compile them, and then maybe move on to doing the makefile and so on. So that's just an idea on how one might approach this. So questions about that, or other questions on PA3?
I'm sure I can pull up the PA3 PDF and find real quick, but for the figure out high and low, did you say that we had to cross-check arg the first and second command line arguments and do a comparison to check which one's higher, or should we just return an error if the second one's not higher than the first?
If the second one is not higher than the first, I think that's an immediate error.
Okay.
But let me pull that up and double check. It certainly should be, because I definitely don't ask you to order them. Although you're coming up with really good ideas in this class for like how I can make future classes work hard. Alright, with two command line arguments, in which case the arguments are the low, high ends. Low must be an integer positive, high is an integer bigger than low. So yeah, they're assumed to be in the correct order. If they're not, print a message and just exit. Alright, cool. Let's go back to talking about GDB. So we introduced the idea of debugging last week, and this notion of, you know, we've got an algorithm in mind, a flowchart, pseudocode, something, right? And we want to execute certain steps, and we convert those into a language like C or Python or whatever, and then we run our program and it maybe doesn't work the way we were expecting it to. And so we want to figure out where the bug is, where the problem is in this code. And the process of doing that, that's what we call debugging, right? Getting the bugs out. Before you can debug a program, you've got to understand what the program is supposed to do. So if you're unclear on what an assignment's asking you to do, writing the code is kind of a frustrating exercise, right? And if it doesn't work correctly and you don't know what it was supposed to do to begin with, that's a really hard situation to deal with. So you want to make absolutely sure that you know what the program should do, right? Now, if you've got, you know, a sample program like you have for PA3 that you can run, you can experiment with that, right? Otherwise, you've got to either dig that out of the assignment description, or, you know, talk to a teacher or something like that. But once you know, okay, if I run this program and I do these things, then that should happen. And you run your program and you do these things, but that does not happen. Something else happens instead, right? Now you got a thing that you can debug. So our general situation is, you know, we run our main program, let's say it's called main, and it's supposed to do X, instead it does Y. What's going on? Why is it doing Y instead of X? Well, I don't know. So you can stare at the code and hope that you see a problem. That's a really hard way to debug. You can add print statements to your program and say, now I'm doing this, now I'm doing that, I is equal to this, X is equal to that, and hopefully, you know, figure out something that's misbehaving. But the other option is to use a debugger. So we're using a debugger called GDB. It's like a new debugger. And here's the basic setup when we use a debugger like this, right? If we just said main, that would run our program, and it would do, you know, whatever it's supposed to do, and you know, have some error or something. GDB is another program. It's a big program. It's written in C, I believe. And when we say GDB main, we're running this program, but we're telling it, hey, I want to debug that program. And GDB will mostly ask us what we want to do. And when we ask it to, it will start executing main for us one line at a time. And we can tell GDB, hey, execute the first line of this program. And it'll execute that first statement. And it'll say, what now? And we can say, execute the second statement. And it'll execute the second statement and say, what now? And we can say, show me the value of C. And it'll print out the value of C for us. And we'll say, okay, execute the next statement. And it'll do that. And we'll say, show me the value of I. And it'll show the value of I. And maybe I's got the wrong value now. So now we've narrowed down the bug to a small region, you know, between lines 2 and 3. Maybe line 2 is a function call. So we can go back and we can say, okay, run my program until you make that function call. And stop at that point. And it'll execute the first few statements, go inside our function and say, what do you want to do now? And we can start narrowing down where this bug might be. But to do any of this, you've got to have a clear idea in your head of what should be happening. And simply, you know, having this thing execute our code line by line is not going to help us debug. What we need to be able to do is execute our program line by line and compare what the computer is doing with what we think the computer should be doing until we find a mismatch. As soon as you find a mismatch, you've got your bug. Alright, so it still takes a lot of work. It takes a lot of understanding of the code. It takes a lot of thinking about what should be happening. Which is why you want to be confident what you think your code is supposed to do before you start debugging it. Alright, we got more people here. Go ahead and send me an attendance note, please. And let's dig into the specifics of GDB. So if this is going to execute our program one line at a time, if this is just, you know, compiled machine code, right, compiled C code, assembled assembly language, this is just ones and zeros, how does GDB know, you know, what the different lines of our original program were? So if we're going to debug, we need to do something special when we compile. When we say GCC, right after GCC space, we put a -G switch. That says compile with debugging options. And so we put in, you know, the rest of our GCC command, but we say -G. That will set things up so that GDB can give us more information about our program. All right, so I'm going to work with some specific examples, and so I have.
Dash G. I'm kind of following along on mine, and so with GDB main it says no debugging symbols found. So if you add the dash G, it'll add those symbols in there.
Exactly. Exactly.
Make sure.
And yeah, that's what it means when it says it's trying to load a symbol file. All right, so I have some programs to mess with. These are versions of our ODP when we were counting the number of E's in a string. And I've written different versions of this count E function inside a file with a main program that calls it. And all of these programs have bugs in them. And these are relatively small programs, so chances are when I show you the source code, you might see what the bug is just from looking at it. I'm going to ask you not to shout it out. Okay, the goal here is to play with GDB and see if GDB can lead us to the bug if we don't happen to be able to see it just by looking at the source code. But you know, these programs are relatively small, so finding the error by looking at it is totally an option. But so here's an example. Here's our count E function, which, you know, loops through the string, counts the number of E's. And here's our main program. I'm going to call count E with a string hello bye. I'm going to save the return value and result, and then print out the result. And this is not going to work the way we want. So when I run it, it's going to tell me, you know, I had 4 million E's in my string, when in fact my string had only 2 E's in it. So there's obviously a problem in my count function. So I want to use GDB to try to understand what's going on. And if I just say GDB main 1, at the bottom of this intro it says no debugging symbols found. Okay, I'm limited in how much debugging I can do. The reason is when I compiled my main program, I didn't have that -G switch. And if you just have an executable file, you're limited in how much debugging you can do. So I'm going to get out of GDB. I'm going to do a Control D, right? And Control D is usually how we quit out of things. Don't use Control Z, because that leaves things running in the background. And Control C, I don't think will work here. Right, it'll just bring me back to GDB. So I'm going to recompile GCC-G, and then the rest of my compile command. And now when I say GDB main 1, it says reading symbols from main 1 done. So I'm all set to go. Alright, so one thing I can do is I can say list, and I can look at my source code inside the debugger. So you don't have to go outside and look at your files in a separate editor. You can do it from here. Limited usefulness, but it's handy sometimes. So here's the first 10 lines of my program that I'm debugging. And if I just say list again, it will show me the next 10 lines. So lines 11 through 20. And if I want to see in particular, you know, line 6, for example, I can say list 6, and it will show, well, that was kind of boring. List 13, and it will show me a few lines before and after line 13. So list is useful.
Yeah, that in itself kind of gives you the opportunity to just look at 10 lines at a time. You might be able to see what it is from there.
Absolutely. And I can also say list and put in the name of a function, and it will show me some statements around that function and so on. So all kinds of things you can do. And there's help available. If you just say help, it invites you to type help on, you know, a category of commands. Or I could say help list and get help on the list command. And there's a lot of capability inside GDB. We're going to touch on a really small set of it, right? But we'll learn, 10 or 12 commands that will be enough to do most of what we have to do debugging wise. Another thing to note is that pretty much anywhere in GDB, if I just hit an enter, it'll repeat the last command. So I just did a list that showed me the first 10 lines. If I just hit an enter, it'll repeat the list command and show me the next 10 lines. And that's useful because, we're going to be executing our code one statement at a time. If our code has, hundreds of lines in it, we're going to type the same command over and over and over again. For example, do the next line, do the next line, do the next line, do the next line, right? So we can just hit enter and it'll repeat our last command. All right. Well, we're looking at our source code, but that's not what we're here for. We're here because we want to execute our program and see what's happening. So to start executing, we type start. And a bunch of things happen here. So the first thing is it says temporary breakpoint at 692 file main1.c line 8. Okay. So a breakpoint is something we can set up in our file which says, hey, if you're running my program but you get to this line, stop. Come back and ask me what to do. If you've done Engineering 270, these are breakpoints in MPLab. Exactly the same idea. All right. So it creates a temporary breakpoint right at the beginning of my program, line 8. Right. If you look at our program, these things don't actually do anything executable at runtime. These are used by the compiler to know how to compile other things. This is just declaring a function. This is where our main program begins. This is part of the syntax of a function. This is the first line that actually executes. So it created a temporary breakpoint at that point. And now it's showing me this line right here. All right. So important thing to keep in mind with most debuggers, including GDB, it shows you the thing it's about to do. It's getting ready to execute line 8. It hasn't executed it yet. All right, so we do start to begin the debug process. And if it hasn't executed this call yet to count E, then result, has whatever value. So we can say print result and see the current value of it. And result happens to be equal to 0 right now. So we can say print variable name to see the value of a variable. We can also abbreviate our commands as long as they're not ambiguous. So we could say p variable, and that will print out the value of the variable. And that's one of the main commands we use is print. So I can just say p result, and there's the current value of result. All right. Now we want to execute this statement. It's about to do statement 8, right? That's what it told us up here. If we want to execute that statement, we can say next. And so next says execute the statement that you're about to execute. And if I say next, it shows me now it's about to do line 9. In other words, it just did this whole statement. It called count E, it took the return value, it saved that in a result. And now it's about to do a printf. So result should have been given a value here. I can look at result, and sure enough, result changed. Now it didn't change to 2, there's a problem somewhere. But this shows me that this statement did get executed, and now it's about to do this statement. And if I say next, it'll call printf, and it prints out result equals, and there's that number. And now it's about to do my curly bracket. Well, what does that mean? It's about to exit from main. If I go ahead and I say next, now something weird is happening, right? I'm in this thing, _libc start main, blah, blah, blah. This is sort of like operating system code. This is the stuff that called main. This is the stuff that caused my main program to begin executing. And it's executing code from something called libc-start.c, but I don't have the source code for that in my directory, so it can't show me the source code for that. But this is debugging the stuff that came before main started running, right? So at this point, you know, my main program is done. It's wrapping up, but it's pretty clear something happened inside my count E function. So I'm just going to start over. I'm going to say start, and it's going to say, hey, you're in the middle of debugging, so would you like to go back to the beginning? I'm going to say yes. And I'm back to where I was a few minutes ago. I'm about to execute this call to my function. Yeah, so really good comment in chat right now. When you have an IDE that, you know, shows you your source code and highlights what line you're on and all that kind of stuff, a lot of times that's built on top of, you know, these command line tools like GDB, for example. If you understand how the debugger is working at this, you know, command line level, that can help you be more efficient when you're working inside some kind of integrated environment where you know, it's all graphical. You double click on a line to set a breakpoint and so on and so forth. So yeah, that's cool. All right. So when you say next, it says go to the next line of my program, right? And line 8 is a call to this function. Line 9 is the print. So if I say next, it's going to do everything that happens in this line, and then it's going to go down here. Well, you know, obviously something is going wrong inside this function. So I want to step into that function instead of stepping all the way to this next line of my program. So there's another command which is step. And we sometimes call next a step over. And we call step a step into. This is terminology from MPLab. Again, if you've done Engineering 270, this is what MPLab calls them. So a step into will say, hey, go into the function that's being called, and let's start stepping through that.
This kind of reminds me of the debugger when you're doing assembly in 270.
Exactly, yeah.
The step into does all the go-to calls. And
yep, exactly the same idea. So yeah, let's do a step here. And now instead of stepping to line 9, it's going to step to line 16, which is the beginning of this function. So now we can start debugging what's going on inside our count E function, because that's where the error is. And it tells me I'm in a function called count E. I was called with an argument at this address in memory, and that argument is equal to the string hello space bye. And it's line 16 of main1.c, and here's what that line looks like. So it's about to start a for loop. So if I print the value of I, it's, you know, 21,845. It hasn't executed this line 16 yet. So let's go ahead and execute that line, and now if I print the value of I, it's 0. It just did this I equals 0. That's good. I can print my argument, that's the string hello bye. I can even do things like say, tell me what the string length of my argument is, and it'll tell me, oh, it didn't tell me, my bad. Oh, string length is not that kind of thing. Forget that. Most functions we can actually call and we can see the result, but not here. All right, but we can look at the value of I. I is equal to 0. I can print out arg bracket I, and that's an H. That's the first character. So this says if arg bracket I is equal to E, increment C. So I'll execute that instruction, and I believe that should not have incremented C. Right? Because arg bracket I was an H, which is not the same as an E. So now if I print the value of C, it should be 0, but it's not. It's some huge number. So let's go back to the beginning. and let's step into our function. And before we execute this for loop at all, let's print the value of C. And it's some big, huge number. And so at this point, probably it's becoming pretty obvious what's going on. Right? In the beginning of my function, before I do any of this code, C has this strange value to it. Why? Because I haven't initialized it. Right? So I said C is an integer, but I didn't give it a value. Alright, so at that point it's like, oh, I get it, you know, I forgot to initialize C. Okay, good. Now I could you know, leave the editor, make that change to my program, recompile, come back in, try it again. Sometimes you can do some of that from inside. For example, I can change the value of C by saying this. For example, I can say print, and I can say C equals 0. Right? And this is an assignment statement. And so it prints out as 0, but now if I print C, I can see C is equal to 0. So I can initialize things like that. So now I can say go ahead.
Does that change it in the program, or that just changes it so you can see if it works?
That just changes it in my current execution of the program. I'm just changing a memory value. But it's
still have to go back and change it to implement the changes.
Yeah, you still have to go back, change the source code, recompile, and so on.
Okay.
Alright, so now I can come in here, I can print out the value of I can print the value of C, I can say execute that if statement, I can print C and see that it's still equal to 0. Now I can print the value of I and see that it's 1, I can print arg bracket I and see that it's an E, so this if statement should increment C, right? C is 0, execute one statement, C got incremented to 1. Now I can go ahead and I can start executing my whole loop. And I'm done with my for loop, right? Well, I'm outside my for loop, so I doesn't have a value, but I can print C and I can see that C is 2. And that's what it should be because my argument had 2 E's in it. So I can say next, I can return back, I can print the value of result and see that it's a 2, and now I can execute my print statement, and hey, there's what I was hoping to see, result equals 2. Alright, and so yeah, we want to get really proficient at this, and if you can make, you know, a change by hand, by just, you know, setting a value of a variable to something else, you can possibly keep going with your debug session. But it's not uncommon that you need to get out of GDB, change your code, recompile, go back into GDB, get back to where you were, and continue. But after you've done that enough times, it gets to be, you know, muscle memory. And you can be prepared when you're debugging, especially for a really hard to find bug. You might do this, you know, 20, 30, 50, 100 times, right? But I mean, if you do this 100 times, you're not even going to have to think about how to get back to where you were. It's just going to be doing the same thing again and again. Some debuggers have options to go backwards, so you can actually like back up and go backwards in time to you know, change variables and then go forward again. That's always a fun thing to try to do. But that's the basic setup, and this is probably, you know, 80% of all the debug commands that we're going to need. The other ones we're going to talk about, and I'll post something on Canvas with a synopsis of these. We're going to want to set breakpoints. We're going to want to be able to examine memory, not so much here, but in CSE222, we'll want to examine memory. And that's probably the bulk of it. We might need to do a watch point once in a while, where we can actually say, watch this variable, and if it changes value, let me know. Alright, so I've got a half dozen broken main programs that we can play with tomorrow, and we'll go through this in, you know, at a faster pace, but look at different ways we can find a program that's misbehaving and use GDB to see what it's doing when it executes and try to find our bugs like that. So that'll be our plan for tomorrow. All right, have a good afternoon. Send me an attendance note on the way out, please, and I will see you next time.